Welcome to Electrostatics. So we're going to do a little bit of review, kind of grade 10, so I don't know if you remember this kind of stuff. You can take materials and you can rub them together, right? And then, you know, like you've all done this trick where the balloon kind of sticks it doesn't stick very well because, it's a ceramic surface with metal behind it, but you get the idea, right? So it's attractive. So first thing I want to talk about is this thing called the triboelectric series. Tribology is a fancy word for the study of friction. So it's like the friction electric series, right? So that's kind of what it means. And so what happens here is when you rub two materials together, depending on like to do the valence shell electron structure and that kind of stuff, and electron affinity, those kind of things, right? Electrons can get transferred from one material to the other. And I've just picked a few here. These are materials, so skin, for example, and it's right at the top here, it can become very positive very easily, dry skin we're talking about here. And down at the bottom, we've got rubber and styrofoam. So when I rub this rubber balloon on my hair, the rubber gains electrons, so electrons get ripped off my hair, and where the electrons go? Onto the surface of the balloon. Sound good? So these materials gain electrons. These materials become positive because they
lose electrons.
Very good, exactly, right? No, you don't gain positive charge, you lose electrons to become positive. Why can we not transfer positive charge?
Can't, because the nucleus is gone.
Yeah, positive protons are in the nucleus. They're bound by the strong force, right? You cannot rip protons out of the nucleus by any human means type thing, right? Other than nuclear reactions and stuff. And so we're always talking about a transfer of electrons. So everything we talk about in this unit is really to do with transfer of electrons. I'm transferring electrons from my hair to the rubber balloon. But wait,
what?
Why does it stick to the wall? The balloon is, sorry, what's the balloon? The balloon's going to be
More negative.
So it's negative. The balloon's negative, yes?
Yeah.
Is the wall positive then?
Yeah.
But I didn't rub the wall with anything. Like,
Might be the material.
what's going on here? Did you do this in grade 10? Why does the balloon stick to the wall? Is neutral, right? Like, I don't feel any charge from the wall.
We did do this in grade.
You did. Why does the balloon stick to the wall?
Is it giving off some of its electrons to the wall?
Just give them off, but I was to draw
Share electrons.
a picture. There's the wall and the side view, and here's like the balloon kind of stuck to the wall. We've just said the balloon's all negative, so it's you know, basically I've rubbed my hair all over. It's all coated in negative. And by the way, it's not a conductor, right? So the problem with things like this is, you know, one region of the balloon might have a lot of electrons stuck on it, and another region might not have much, right? It's not conducting. So it's static electricity. It doesn't move. But in the wall, like for a negative balloon to be attracted to a wall, the wall's got to be positive. Yes, does that make sense?
Mm-hmm.
Good. I'm not trying to trick you or anything. How does a wall become positive?
It's
by giving
electrons to the balloon.
Well, but then it would neutralize the balloon and it would fall off the wall. So you know it's not good thought. You know it's not ripping electrons off the balloon trying to balance it out. It can't. And this surface is ceramic, it's glass. It can't even, electrons are stuck in there. It's not a conductor. Huh.
What's happening?
What is happening? Well, what do you know about the structure of materials? If you look, in on an atom or a molecule, where's the positive charge?
In the nucleus?
Yeah, the nucleus. So I'm going to do a big scaled up version, but let's pretend these are like the atoms or molecules in the wall. Where are the electrons? Yeah, around them, right? Kinda. Well, but now you've got an electric field being generated by this balloon. What's going to happen to the electrons in the wall?
Disperse. Repel.
Yeah, they're repelled, right? The electrostatic force between them. And so, again, this is a hand-waving argument, very generalized, but generally the electrons, which were kind of all over the place, now tend to move just a little bit further away than they were. So, and again, in this very kind of simplistic argument, they're still there. The wall's still neutral, but the electrons have been repelled. And of course, the distance between these two is now, on average, going to be slightly greater than the distance between these two. What do you know about the electrostatic force from last class?
It's over r squared, so it gets.
Can you see this on the video?
Yep.
What's the equation?
K QQ over r squared.
Yeah. So it's an inverse square law. So if one of those distances is even slightly bigger than the other, because it's an inverse square, the effect on the force is that much bigger, right, with the closer one, because of the inverse square law. It's not a linear relationship. And so there's quite a strong relationship between distance here. So if you can move those negatives even slightly further away, it appears like the surface of this wall is slightly positively charged. That makes sense? This is called charging by induction, where you haven't really changed it. You've just induced charge by making the electrons move a little bit further away. Okay, that makes sense? And it's actually, it commonly occurs all over the place. It's kind of, like you can move charges around pretty easily that way. Okay, so we've got this idea that, the wall is neutral, definitely neutral. It's still, it's still got the same number of positive and negative. We just move the negatives away. How do we move the negatives away?
Is it repelling?
Yeah, there's a repulsive force there, which then exposes the attraction. Wow, that's kind of cool, right? So, on this series, can anyone give me some examples of this in daily life where you see this happen? Maybe weekly life. That's how often you do your laundry.
Oh, where
Oh,
like
yeah.
shockers sticking to each other?
Yeah, you ever pull clothes out of the dryer and they're like, wow! Oh, what are your clothes made out of? Cotton?
Plastic.
Your clothes made out of plastic? What are you talking about?
It's polyester.
Yeah, like probably most of your clothes these days are actually plastics, right? That's what the problem with microplastics, right? Is when clothes break down, those little pieces of fabric, like where's that stuff go? It's not natural, right? It's plastic, it goes into the environment. Anyway, yeah, your clothes like polyester, rayon, or we call it bamboo fiber now. It's chemically treated, it's turned into a plastic. It's a long chain polymer. Anyway, a lot of our clothes are actually made of plastic. So yeah, they diverge on the surface. And of course, if it's wool, hair is a form of wool, right? That kind of stuff, even further apart. And so, and then of course your skin, you go to pick these things up. You ever notice they like stick to you and stuff? Again, it's induction charge, right? You're not charged, but as you go to pick those clothes up, it pushes the electrons away in your skin. Your skin becomes positive very easily. There, you get the idea. Okay, so that's kind of the idea of charging stuff by rubbing it together. You can stop the video. Thanks.